Welcome back to the tutorials for zero energy building. This is tutorial 1b, and we're going to talk about benchmarking and utility bills. In this case, as you start your initial energy model, the purpose of this part of it is to be able to understand the numbers with a little bit more context. So as you model how the building will, or how much energy the building uses, it's going to be useful to know how much energy the building actually uses, and how much energy similar buildings use. So I'm going to walk you through how to approach this. You've already looked at power and energy metering, and by now you're a master at the difference between power and energy. And so on the second page, you can see the requirements for this part of the assignment. And this tutorial is just going to be about this energy bills and benchmark portion. And the next tutorial will talk about the energy model itself. So I'm going to go back to the Excel spreadsheet that you started working on with the power metering. And let's go to the next tab, Energy Models Template. And in this template, I'd like you to fill out this whole worksheet, and this is going to help you to generate your model. In this tutorial, we're just going to cover number 1, basic information, number 2, energy use from utility bill, and number 3, energy use from the benchmark. So let's start. Make sure that you put in your name here, your author, and the building area represented by your utility bill. In this case, I'd like you to fill out whether, I guess it's going to depend on whether utility bill is for a representative area of the building, such as like the 33rd floor of a skyscraper, or if it's for an entire house, or if it's for a unit in an apartment building. And so it's important that you understand whether your utility bill is the same or similar to the analysis area that you're looking at. In this case, my utility bill and my analysis area are going to be exactly the same because I'm going to be looking at my apartment. And my utility bill is representative of my apartment, which is about 100 square meters. So I'm going to put that in for the building area represented by the utility bill, and I'm also going to put that in for the analysis area here. For the electricity cost and the fuel cost, you're going to need to use your energy bill that you collected in the documentation stage. And I've got here a sample utility bill, and this one is on the left a gas bill for May 2015 to June 2015. On the right is the electricity bill for May 2015. So let's see. This is asking for your electricity cost in US dollars per kilowatt hour. If I go over here to the electricity portion, I'm going to zoom in here so we can see this better. And you can see that the Tier 1 allowance is for 224 kilowatt hours, which is here, and that's at 16 cents a kilowatt hour. Tier 2 usage, which occurs once you exceed that Tier 1 use, is 43 kilowatt hours at 18.6 dollars per kilowatt hour. And probably most of you have some kind of tiered system. It's usually not just a flat rate, although a flat rate would be much easier to calculate. In this case, we're going to take a weighted average by just taking the total, which is also including some tax, but that's okay. Let's include everything, as $44.74, and then the total energy that we used was 224 plus 43 is 267. So if I divide 44 divided by 267, I should get the number. So again, to make a formula, press equals, and then I'm going to divide 44. Let me try to be more exact here. It was 4474 divided by 267 kilowatt hours, which gives me 17 cents per kilowatt hour. Now keep in mind, if you're working in another currency, please convert to US dollars so that we can compare across the whole class. Now, on the gas side, we've got here Tier 1 use 14.95 therms, which is a little bit of a different unit. It's a unit that we can convert to kilowatt hours. In the US we use therms, and sometimes in the United Kingdom they use therms, and most of the rest of the world doesn't. Most of the rest of the world uses different units. Actually, it's wildly inconsistent depending on the type of fuel that you have. And so what I've done here, going back to the Excel spreadsheet, if you go to the tab down here that says fuel conversions, I've listed some common fuels and some conversions, so or units and conversions. So 1 cubic meter of natural gas is equal to 11 kilowatt hours. So if you type in here 100 cubic meters of natural gas, you'll get, if it does that, you can make the column bigger. So 1100 kilowatt hours. So this is kind of an interactive conversion template, basically. And it says here that 1 therm is equal to 29.3 kilowatt hours. In this case, for this bill, we have 14.95 therms plus 8.77 therms plus, that's from May, that's just in May, and then we've got a little bit extra here, 5.85 and 3.43. The total actually shows up right here as 33 therms, so that's what I'm going to divide by. I'm going to divide 44.47 divided by 33, and I'm going to do that right here. 44.47 divided by 33. No, shoot. No, not. I'm going to type in 33 therms because that's what I want to convert to get kilowatt hours. And then I'm going to divide 44.47 divided by this number of kilowatt hours. So to do that, I've got a formula, and then I can click on that cell, and it divides everything for me. So it comes out to 0.046 kilowatt hours per for gas. So I can go back over here and type that in. Is it 0.046? I think I did that right. Yeah, kilowatt hours. Okay, almost there. The next bit is designed to help you understand what it means to generate energy on site. So as we're using the energy, it's also useful and interesting to know how much you could generate if you had, say, a photovoltaic array. And this is a very quick and easy way of getting a first pass. And I'll show you how to do this. What it's asking for is the annual horizontal solar radiation, and it says reference the solar radiation sheet. So go down here to solar radiation, and you see a map of the world. And again, this is a very gross estimate, but this map of the world is color-coded by annual global horizontal irradiation, which you see up here. What global horizontal irradiation is the amount of solar radiation in kilowatt hours that falls onto a horizontal plane that's 1 square meter by 1 square meter, 1 square meter in area. And so, for instance, if you take here where we are in California, you can see it's kind of orangey yellow. Let me zoom in there. Orangey yellow. And then if you zoom back out to our chart, orangey yellow is somewhere around 1600 kilowatt hours per square meter, right around there. If you're in Northern Europe, it's green, so that's probably more like 1100 kilowatt hours per square meter. If you're in Northern Australia, this looks like closer to 2200 kilowatt hours per square meter, etc., etc. So take a guess, your best guess based on where your case study is. I'm going to go ahead and use 1600 kilowatt hours per square meter, and then come back to the energy model template and enter that number in here, and this will automatically generate for you, using a formula, the potential electricity generation for a photovoltaic panel that's horizontal. And you can see actually from the formula here, this is a very simple formula. It just takes 1600 multiplies by 15%, which is a basic rule of thumb for how much electricity a photovoltaic panel can generate in AC, alternating current. And we'll talk more about photovoltaics later in the semester, and I'll show you a much more complex and accurate way of doing this. But this is a really good rule of thumb for now, and it really goes from base principles. And you'll see when we do the energy model how this is going to relate. Okay, so now that we've got the basic information filled out, let's go down to the energy use from the utility bill. And here we're asking for both fuel and electricity. Most of you will probably have one or the other or both. And what this asks for is the annual energy use in kilowatt hours per year. I've got here a bill that is, this is the bill that I was just showing you. I only have 1 month actually. Your documentation should have at least 3 months that are representative of your climate. And if you only have 3 months, say you have January, June, and March, then what you should do is take the totals from each and multiply by the months, the number of months that are similar. So this one is a May month, and in the Bay Area, I'd say April, May, June, July, and August are very similar types of months. The climate is very similar. So that's 5 months. So I could take this total energy use for gas and electricity and multiply by 5 and get those months. And then for the other months of the year, I'd want to take representative bills from those. Alternatively, if you have bills for every month of the year for a whole year, that's probably a better, more accurate way of doing it. So let's start with electricity use. I've got here 267 kilowatt hours that were used in May, and so I don't have, that's all I've got right now. So I'm going to take that 267 kilowatt hours and then multiply by 12, 267 times 12, to get a total for the year. For the fuel, remember it was 33 therms, and this is asking for kilowatt hours. So I'm going to go back over to that fuel conversions. I still have 33 written here. That was 967 kilowatt hours. And I'm going to type in 967 times 12 there. I forgot the equal sign. There. So that gives my total. And these fields over here will automatically populate based on the values here. And if you want to see where it comes from, all you have to do is click on it and then click up here, and then it will color code. So what it's saying is it's taking 11,000 kilowatt hours per year and dividing by the area of the bill, or 100, to get an energy use intensity, kilowatt hours per square meter per year. Press enter and you can see what that number is. So 116 kilowatt hours per square meter per year just for fuel, and 32 kilowatt hours per square meter per year for electricity. Now this gets really interesting when you start looking at cost, because you see in this particular example the fuel cost is about a third of the cost of electricity. So although I'm using roughly 4 times more fuel than electricity, the costs turn out to be very similar, about $534. And this is a good way of just kind of getting a sanity check as well to see if this feels like it's a realistic number for the amount that you would pay in utility bills. So in my case, this is just over $1,000 a year, which translates to just under $100 a month, and that's pretty reasonable for a 1,200 square foot, 100 square meter apartment. And then this final category here explains the photovoltaic panels. So this is taking the annual energy use there and dividing by the annual horizontal PV generation, and then dividing by the area of the zone. And what this is giving you is a ratio of, click here, it's a ratio of how much PV area you would need in order to offset the energy use of your zone. In this case, I would need half of the area of my zone in PV. So this means that if I had a 2-story building, I could effectively get a zero net energy building because I'd have, well actually this is just a little bit over, because if you add these, it turns out to be 0.61. So I wouldn't be able to get a zero net energy building with a 2-story building. If it were a 1-story building, and the PVs were just on the roof, horizontal, as we discussed before, then those PVs would take up 61% of the roof. If you have any questions about that, bring those questions to class and we can talk about it more then. Okay, so let's move on to the last part of this video tutorial, which is going to be about benchmarking. And a benchmark is very simply a comparison to a baseline or a model or even the utility bill. It's a set of buildings that have been either monitored or modeled that are reasonably similar to the building that you're looking at. And I know that many of you are coming from different places and a lot of people outside the United States, and I'm going to show you 2 benchmarking tools that are United States specific, and I'll show you how you can use them for things that are outside of the United States. I also want to open this up so that if you find or know of good benchmarks in the place where you're from, to please use those. I think it's climate and building culture are 2 of the most important things to understanding building energy use. And when you look at different climates and different cultures, it makes it relatively difficult to benchmark. That being said, there are some interesting ways that you can start to benchmark buildings that are that use analogous climates or cultures. So let's start. I'm going to start first with commercial buildings, and then I'm going to talk about residential buildings. They're 2 kind of different types. You see in the assignment on the first page, I've got 2 links, one to residential benchmarks and one to commercial benchmarks. So let's first go to the commercial benchmarks. And let's see if this launches. This should take us to a building energy data book that was developed by the U.S. Department of Energy, there it is, using a data set. Now this data set is actually quite old. It's from 2003. The new one should be coming out any day now, but unfortunately it hasn't been parsed yet. But they do update this from time to time. And this data set is looking at, it's called the Commercial Building Energy Consumption Survey, where they went around and asked people about their buildings, including how much energy they use, what kinds of energy they use, what types of buildings they are. And actually you can see all of the different components of the survey here, the location, where in the United States it is, what climate in the United States it is, what's the building type, what are the characteristics like, when was the building built, who owns it, what's the square footage, number of floors, HVAC systems, heating systems, percentage glass, roof construction, building shape. It goes on and on and on. And all of these things are important factors in energy use. And I want to show you here what this does, what this database allows us to do is to search for particular characteristics. However, it has some limitations because it's not a huge database. I want to give you an example of that. So let's start at the beginning. Climate and building type are probably the two biggest determinants of energy use. And so the first step, if you're going to use this for a building that's not located in the United States, is to find what an analogous climate is. And I'm going to show you this using this climate data here. You can view the map, click there. It gives you a map of the United States. And it's zoned out into a cold region, a temperate region, a region with cold winters and hot, humid summers, warm summers, a warmer region that's yellow, a mild warm region here that extends into California over on the west, and then a hot, arid, dry region, which is the southern belt of the United States. And these four climates are indicative of a lot of climates around the world. So if you were, say, in Beirut, Lebanon, you might choose a yellow climate here, zone 3. Or if you were in, say, Sydney, Australia, you might choose an orange climate. Or if you were in northern Russia, you might choose a blue climate. Let me explain what these zones mean. Zone 1, the blue climate, is less than 2,000 CDD, which is cooling degree days, and greater than 7,000 HDD, heating degree days. So you can see that most of the days are for heating, and very few are for cooling. And it kind of progresses down the list. Let's take California as an example, since that's where we are and the course is being held here, which is zone 4. It has less than 2,000 CDD and less than 4,000 HDD. It's a relatively mild climate. And if I just press that, 2,000 CDD and 4,000 HDD, let's not narrow our factors any more than that. Let's just look at that and press search, and it's going to show us results for that search. It includes the sample size, which is very important. There's 1,274 samples in this, which are representative of 1.3 million buildings in the United States. And it gives here, let's go down to this, end uses: heating, cooling, ventilation, water heating, lighting, cooking, refrigeration, office equipment, computer use, and miscellaneous. And most importantly here, it gives you 1,000 BTU per square foot, which we can pretty easily translate into 1,000 of watt hours per square meter. And I'll show you how to do that in a second. But notice this sample size, 1,274. Now let's go back and select a building type. Say, let's go with college building. So if we were going to model Worcester Hall, we might start with a college building. And now let's search this one. Immediately you see that the sample size has dropped way down to only 35 buildings. And now this becomes statistically important, because if one of these 35 buildings that's in the survey is very weird, very an outlier, then it can skew the results. 1/35 of the results can make a big difference. And it's interesting to note here, if you look at the total, let's look at the total electricity use per square foot, or all major fuels, here it is, all energy use is 128.88. And if you go to If we unclick that and go to the larger database, we're at 78,000 BTU per square foot. So it dropped quite a bit when using a much larger sample size, presumably because some of those 35 buildings were much higher energy use. So this is where you have to be careful. It's tempting to go through and click everything possible to get the narrowest possible definition. And if I do that, click on college, and then I click on Worcester Hall, I think was sometime in the 60s, and I click on 100,000 square feet, and I say it's owned by the state government, and it's, was it 9 stories, and on, and I search, it's going to tell me that there's no results because there's nothing that fits that description exactly. So the trick of any benchmarking is to find the best possible data set that is still statistically significant enough that you can draw some conclusions. And in this case, I would say you want to make sure that you've got at least 50 to 60 buildings in the data set. So instead of clicking college here, I'm going to just click education. So that's going to include high schools, preschools, elementary, etc. And I'm going to unclick all these other ones and see if I get a wider range. So 174, that's a pretty good data set. I feel much more confident in that. Of course, it includes a lot of buildings that are not like mine, but at least it's a statistically significant number. Okay, so once you've narrowed it down sufficiently to get a good sample and a good benchmark one you feel comfortable with, then what you want to do is take these end-use numbers, and you can just highlight them like this, press Control-C to copy them, and then maybe what you should do is copy them into a new sheet on your spreadsheet. The way to do that is to press this little plus sign like that, and press Control-V will copy them in. And I can drag these cells to get a little bit more room. And now remember that these are, I'm going to insert a row here. This is in thousands of BTU per square foot. And what I want is kilowatt hours per square meter. And to look for the conversion between BTU and watt hours, I can go to fuel conversions and look for BTU. Here's 1 BTU equals 0.29 kilowatt hours. So to make that conversion, what did I say it was? 0.29. I press equals, and I click on that, and then multiply by 0.29, and that's going to give me kilowatt hours per square foot. And then I can multiply that by 10.76 to get kilowatt hours per square meter. And a handy trick here is when you have all these insignificant digits, you can go over to this tab to format the cells and rein in those digits. Another trick is if you want to fill down, you can drag that bottom right corner and it will automatically do a smart fill, and you can see if you click on the formula that it propagates down. That's pretty neat. Another trick that's kind of fun is if you click on double click on the bottom right, it will do the same thing for as many rows as it can find. So that just fills out our form for us. And now this is a formula here, and gives us the results that we ultimately are going to want to input here. So for space cooling, I'm going to copy this list so that we can compare them. One's on the left. So I'm going to start with cooling, I'm just right-clicking and pasting here quickly. Cooling, heating, ventilation, then comes lighting, then equipment, which is actually all three of these categories of equipment, and then process is process a little tricky. It's any use that is a little bit out of the ordinary or atypical. Typically uses that have very high loads that are not consistent throughout the year, and that's called a process load. It can be tricky to identify process loads as compared to equipment loads. Equipment loads are going to be more consistent loads and usually lower loads, things like office equipment and computers. Miscellaneous in this case is used as a stand-in for equipment loads in the database. So in order to come up with an equipment number, we're actually going to sum these three uses together. And there's a neat little formula for doing this, which is up here in the upper right. There's this auto sum feature. So if you click on a cell and hit auto sum, first it automatically looks. That's not what we want to sum. We actually want to sum these three right there. So that's our sum of 16 plus 9 plus 2. And then if we want to sum cooking and refrigeration, we can drag that. So 6 plus 3 is 8 because of rounding, presumably. Yeah. So it wasn't really 6 plus 3, it was just rounding weird. So then to generate this, what's going to be required in the energy model or the benchmark model, we basically want to have these numbers. So these numbers I'm going to just copy by pressing Control C. And then when I paste it, this is a little tricky as well. I don't want to paste the formula. If I paste the formula, it's going to be reading this, so it returns all zeros. Instead, what I want to do is just paste the value. By doing that, you click on the cell, right-click, and then where it says Paste Special, you go and paste the value, which is this first one. You can also go here. It's a little easier to use in this chart. I want to paste just the value there and hit OK, and now it just paste the value, which you can see it's not rounding. It's only rounding in this. This is called formatting that determines the rounding. Alright, so then the equipment is 27. The cooking is 26, or 2.6. Oh, sorry, I messed that up. The cooking and refrigeration together are the process loads. That's 8.2. And then water heating is 22. If you don't like doing all this cutting and pasting and stuff, you can just manually enter these numbers. That's fine. And then to copy them over to the other spreadsheet, you press Control C and then click over the energy model template. We're going to paste them into this energy use intensity column, and you can do this by right-clicking and then pasting in just the values, so you save the formatting. Now what happens is these other two columns will automatically update with formulas. However, please be careful of these two yellow highlighted cells in particular. Let me explain. In this column, this is going to be calculating the dollars per square meter of energy cost for each of these end uses. So, for instance, the first one, space cooling, has a dollar per square meter cost of $5.98 based on the energy cost times the electricity cost. The next one, however, this yellow highlighted one, is space heating. And space heating can be done with electricity. It's often done with fuel, like gas or propane or kerosene or even firewood. and that will typically be in a different cost category. And so what I've done here is linked the cost for space heating to the fuel cost. Now, if you've got electric heat, you can change this by simply dragging this up to electricity, and then it will automatically update for you the electricity. I'm going to move it back down to fuel. And the same goes for this row. You can see I've linked that to the hot water heating, which is also usually fuel, although it can also be electricity. Alright, I hope that's clear. And then finally, the zero net energy PV area. This is the same calculation as we did up here, but now it's looking at all those different end uses. And so it's worth pointing out, if I go all the way to the bottom of this spreadsheet, I've got a bunch of graphs here, and I'm going to zoom out so you can see them all. There's 3 sets of graphs. The first one is energy use intensity, so kilowatt hours per square meter, and it reports the utility bill as well as the benchmark, as well as the model. I should point out we haven't gotten to that yet. Then the second one reports cost, so the utility bill and the benchmark. And I see that this is actually wrong. I'm going to have to go and correct this. This should be dollars per square meter, and this is just plain old dollars. And then down here, the PV coverage. So you can see the PV coverage for zero net energy that the utility bill implies, and here that the benchmark implies. And you can compare that. I've set up these graphs to automatically update, so you can see that the utility bills are suggesting a coverage of 60% of the roof area for a one-story building, whereas the benchmark implies 100% coverage for a one-story building. So we have one more topic to cover, which is residential energy use. And actually I should go back to the original assignment here, and you can see I've got some residential benchmark, a link to residential benchmarking website, which is this site hosted by the US government again. And this works slightly differently than the commercial website. And I wanted to include this as a different thing so you could see the different ways of benchmarking. That first way, that survey, gave you kind of check marks in a way of understanding, in a relatively transparent way, what the peer group of buildings was like. This one, which is an excellent way of benchmarking residential energy use, is fundamentally different. And so I want to walk you through this very quickly. Much like in the commercial benchmarking program, it starts with understanding your location, and the easiest way to get into this is to enter a zip code. Now, if your building is located in the United States, then the zip code should be easy to find. If you're outside the United States, then the trick is to find a similar climate in the United States and then find a zip code for it. So one way would be to look at that climate zone map that I showed you from the commercial database or commercial survey. If you know of a climate that's similar, then the easiest way to find a zip code for it is to Google it. So I'm going to just look at Oakland, California, and go into Google Maps. I'm going to go into Google Maps, and I'm going to just pick a location and find the zip code for it. So if I zoom into Oakland here, I can click on the map, and down here it'll give me a zip code, so 94612. And that's as good a method as any I can think of for finding a zip code in an analogous climate zone. So 94612 in this case, and it will start to set up this almost like an energy model, but it's actually benchmarking off of known data. And you can fill this out in as much or as little detail as you like. In fact, I think it's always interesting to fill it out once with a lot of detail and once with no detail in order to see what the differences are. I'm going to first do this with no detail so you can see what I mean. Just by having Oakland, California, it automatically populates a few things. It says the house is built in 1968. It says that there's one person between 6 and 13 years old and two between 14 and 64, and it assumes what the energy prices are. And that's as much as I know about it. I'm going to go ahead and press calculate. So this is going to calculate whatever it's going to calculate. And you'll see this actually gives you a pretty good description later. But based on just that information, it comes up with a dollar value for heating, cooling, hot water, large appliance, small appliance, and lighting. And we can translate this into energy use. And the easiest way to translate it actually is to go to this report and have it generate all of these components to the report. It'll make a PDF that's pretty easy to flip through. So save as PDF, and it takes a second, so I'm going to pause this and we'll come back. Okay, we're back, and it made the report, it made it into a PDF, and I'm going to download the PDF so that I can see it a little bit better on the screen. And so here it is, and we can flip through it, but actually it tells you some pretty important information about what the assumptions that it's making. So it gives you the city and state and year, the people living in it that we just talked about. It gives you the energy prices. It gives you the building design. So it says that there's no foundation, that there's an unconditioned attic, that there's a certain code for the wall insulation, there's no weather stripping, etc., etc. So it outlines exactly what the assumptions are for the house and the assumptions for the appliances. And then if we keep going down here to the next page, it gives you that same page with the dollar values. We're going to skip over that. This is the page I want to show you with the results for the whole house. It gives it to you both in terms of electricity and natural gas, as well as breakdowns for heating, cooling, hot water, etc., with the existing home and how much energy, so 469 kilowatt hours of electricity for heating and 501 therms for natural gas. It also gives you what you could save, and there's a whole section at the end of this report that talks about savings. So if I were just going to use this, I could input these numbers directly into my spreadsheet, and where I have large appliances would be process loads, and small appliances would be equipment in that sheet. And I think that's most of what I wanted to direct your attention to. There's a lot of interesting things in this report if you want to read through it on your own. So let's go back though, because what I also want to do is to start over here. What was the zip code? It was, now I'm at 94607. We'll use that. It's basically the same, I think. And now if we go into a little bit more detail, we can select quite a few more options, including, I think if you go to the detailed input, it will give you a whole lot more options. So I'm going to skip over the first part. I can say now the house was actually built in 1996. There's 2 people living there between 14 and 64. Click next, and now it's going to let me input the size and shape. I'm not going to go through this right now, but you can choose to go through this on your own. And actually on the left-hand side, you can see all the different measures that it's going to ask you to input. And this can be quite time-consuming. It's kind of an energy model in its own right. Although not terribly accurate, it's based on benchmarked data from other buildings. So you can input all of these other things. Now keep in mind, when you don't input it, the model or the benchmark is assuming something. We don't know exactly what it is, but some of these defaults are probably what it's assuming. So it's interesting. It's not a black box. It sort of tells you what it's doing. And you can tell it how much weather stripping you have, the types of foundations, and keep in mind we're going to go over all of these different inputs later in the semester. This can be quite time-consuming, and I don't mean for you to go through all of this right now. If you're really curious, though, by all means, go for it. So hopefully this gives you a good overview of the process, and this will be enough to work with so far. It kind of depends on your level of understanding and your background with both architecture and energy for you to be able to even fill this out right now. By the end of the semester, this will be easy stuff for you. So I think that's a good overview of the benchmarking and utility bills, and I'll leave it there. And in the next video, I'll show you how to go about filling out the rest of your energy model.